Alright, hello everyone. Today we'll be doing practice homework 3 in Stata. You can find this PDF with the questions on Blackboard along with the data file stockton2.dta. We're looking at houses sold in California in 2005. We'll be comparing a couple different models, including the log linear, the log regression, seeing how they fit our data, comparing the R-squared values, checking our normality assumptions for each model, and then we'll be doing some predictions and forecasting. So first things first, let's just open the data in Stata. So when you open it, when you click on the file, it should open in Stata, and you should get the file path here. It's a quick way to get started, or just find the file path and use this use command. And we want to clear any data we had there before. So let's go to number 1. Can't spell number. Okay, so number 1, it says estimate the log linear regression model. Ln price equals beta 1 plus beta 2 square feet plus our error. Interpret the estimated model parameters. Calculate the slope and the elasticities at the sample means if necessary. So let's do a little review here. And we have a log linear model. That means we have a log of our dependent variable. So that's going to change our coefficients and how we interpret them. So our beta here will be similar to a semi-elasticity. So if we multiply beta by 100, then we'll get the percent change in our dependent variable price given a 1 unit of 1 square foot increase. But they asked us about the slope and the elasticity. So when we solve for the derivative here, we take the derivative and solve for it, then we get it's actually equal to our beta times our dependent variable. So our slope here, our marginal effect, depends on what the y value is, the price here. And then the elasticity will be our beta times our x value. So keep that in mind. And that's going to change as we change our model. So let's start with number 1. We got to estimate the log linear regression model. So first we need to create a variable that is the log of our price. So we're going to generate, call it L price equals ln of price. That should give us, so if we open our data, we have all of these variables that we imported, and then this one L price that we created. For each observation, each house, we have the log of the price there. So when we regress L price in square feet, then we'll get our log linear regression model. So here's our beta 2, here's our beta 1. Remember, if we multiply this by 100, we get a semi-elasticity. But we want to find the slope and the elasticity here. So the slope depends on price, and the elasticity depends on square feet. And if we look back at the question, they said at the sample means. So let's figure out what the values of our sample means are. So we're going to do summarize, price, square feet. And we get the mean price is 112,810.80 cents, and the mean square feet is 1,611.96 square feet. So to find our slope, we will multiply our beta. So our beta 2 is here. You can just copy that right in there for simplicity. And then we have our sample mean. And then when we run this, it should tell us that our slope is 67.23. That means for this model estimates that every increase in square foot is associated with a $67.23 increase in price. So then if we find our elasticity, we do that by multiplying our beta with the sample mean square footage. Nope, we added them. That's why we got a weird value right there. So here we get 0.9607. So that tells us for every 1% increase in price, or in square footage, sorry, we get a 0.96% increase in price. Okay, so again, I won't be writing everything out in Word, but I will give you the Word document so you can see some examples of the interpretations and how your homework 3 should look. So let's move on to number 2. Estimate the log-log model. ln price, ln square feet are variables, and interpret the estimated model parameters. Calculate the slope and elasticities at the sample means if necessary. Okay, we're gonna do it. So number 2. Now we need to make a log of square footage variable the same way. Regress price of square feet. So we got to run both of these. Have a variable in there, and then when we regress it, we get 1.0065. Okay, so the thing about the log-log model is it gives you the elasticity directly. So here we're gonna say that according to this log-log model, a 1% increase in square footage leads to a 1.006% increase in price. So if we want to find our slope, we've got to multiply this value by price over square footage. So let's do that. Let's see what we're looking at the means again. So we have this, and then display slope equals our beta times price over square footage. So here's our mean price. Here's our mean square footage. And we get 70.443. So that was pretty similar to the last one, but again, we're using a different model, so we're going to get slightly different estimates. And then we can write out what our elasticity is. Remember, you can refer to your regression directly. Sometimes it's a little hard to remember how to do that, so I'll show you right here. So this is how we access this coefficient. Underscore b and then the name of the variable. So we get our elasticity is 1.006. So that's slightly different than our 0.96 earlier, again because we're using a different model. Alright, number 3, compare the r-squared value from the linear model to the generalized r-squared measure for models in part 1 and 2. Alright, so for the linear model, it gives us the r-squared directly. So we can just regress price in square feet, and then here we get the r-squared right in our regression output. It's 0.6721. Now this is telling us the amount of variation in price that is explained by square feet. That's explained by a model. So if we have a higher r-squared measure, then we'd say our model is better. It better explains the variation. To do this for a log linear model or a log-log model is not as simple. So we have a generalized r-squared measure, and it's something like the correlation between price and our prediction of price. So first we need to create a prediction of price. We'll call it price hat. But if we look at our lecture notes, you can see that we're going to need to take the exponential since we have a log linear model, and then we also have to add in this sigma hat squared over 2. So that's just part of the corrected prediction based on the log normal distribution. So basically this is what we're going to have to code into Stata. So let's keep it organized. R squared for our log linear model. So the first thing, we need to get the right model into our memory. Alright, now we have that, we can create a local variable called sigma squared. And this is going to be based off that regression output. So our sum of squared errors divided by sample size minus 2, so that's the degrees of freedom, and then we can generate our price hat corrected measure equals exponential of our constant plus square footage times square feet plus that local variable sigma squared over 2. So when you run this, so it's saying that it's not found. That's a very common error. So it's because this sigma squared is a local variable, so you have to run it all at once so that the sigma squared is still in memory when it tries to run this generate command. And then now we should have price hats corrected. That's our log linear. So that's should be in our data set now. We can find the correlation between price and price hat corrected. And then say display generalized squared measure for log linear model is that correlation squared. So that we get 0.7147. So we can already compare that to our linear model. So if we can't find it, just run it again. And we can tell our R squared is better with the log linear. Now let's do the log. So we can just copy, paste this whole thing. Let's make sure we change our regression to the L square feet. And then this is our log model. And sigma hat squared should stay the same. It's just based off a new regression. We want to make sure we store this as something different. So we'll say price hat C2 is our predictive value for our log model. And here we need to change this to L square feet and L square feet because our explanatory variable is now the log of square feet. So if we run these, everything's good. We get the correlation, and then we can get our generalized R square by taking that correlation and squaring it. So if we compare this, 0.714, 0.714787771, it's the same. It's actually the same because I messed up here. I put the wrong variable into this command right here. We should have price hat corrected number 2. And if we run that, we get 0.672, so that's a lower than our previous measure. So it looks like the log linear model is giving us the best fit in this case. Okay, so let's move on to number 4. Construct histograms of least squared residuals from each of the models in part 1, 2, and 3. Obtain Jacques-Barra statistic. Based on your observations, do you consider the distribution of the residuals to be compatible with an assumption of normality? Okay, so what we're going to do here is for each model, let's start with the linear model. I'm going to regress. From there, we can get our predicted y values. So I'm just writing this in kind of backwards, but it doesn't matter. Now we have y hat 1, that's our predicted values for our linear model. And then from there we can find our residuals for our linear model, and that's going to be the observed price minus the y hat 1. And then once we have all those residuals, we can look at them by just saying histogram resid 1. So this will give us a histogram. Or we can just copy this and put that into our output. If we look at this histogram, we see some skew over here. So there's looks like our residuals are not exactly normally distributed. So we can check that also quantitatively with the Jacques-Barra. So first we want to summarize the residuals. Detail. And then from that command we can calculate our Jacques-Barra statistic. And you can find this formula in your notes. So this is for a linear model. This would be R of n, so our sample size from our regression, over 6 multiplied by skewness, and the skewness is coming from this detailed summary output of the residuals. So looking at the distribution of the residuals, plus the kurtosis minus 3 divided by, squared divided by 4. You get 2,455. That seems really large, but our residuals didn't seem very normally distributed, so it makes sense that we get a large number here. So now let's do this for the log linear model. We already have the prediction from up here. That was price hat corrected. So let's use that to generate our residuals. So first let's get the resid 2 is y hat, price hat corrected, price minus price hat corrected, so the difference between our observed value and predicted value. And we're going to histogram resid 2 we get, looks a little bit more normally distributed, and then we can find our Jacques-Barré statistic without changing anything except the residuals that we're summarizing, and we get a slightly lower number, or pretty significantly lower. So it seems that our log linear model is better than our linear model in terms of the normality assumption of the residuals. And then we'll just change this to replicate the process for our log-log model. Okay, so that's already defined because I did it earlier. But we get our histogram of residuals, and it looks less normally distributed. There's more skew up here. And we get a Jacques-Barré statistic that is much greater. So the log-log model doesn't seem to conform with our normality assumption of the residuals. And we can compare this if we want to make a conclusion about whether this fits our assumptions. You can compare this Jacques-Barré statistic to the chi-squared critical value with 2 degrees of freedom and alpha 0.05, and this is inverse chi-squared tail 2.05, and we get something around messed up. Got a dot instead of a comma. Oops, I placed the wrong one. Alright, and we get something around 6. So none of these models confirm with our normality assumption. We reject the premise that our residuals are normally distributed, but we can see that our log linear model is the best in terms of conforming to that assumption. So number 5, it says for each models plot the least squared residuals against square feet. So it's going to be easy since we already have our residuals stored in our data. So what we want to do is just make a scatter plot. Residual 1 with respect to square feet, and we're looking at how these residuals are changing as square feet changes. So as square feet gets larger, we see more variance and even some bias. So some really large numbers up here, you don't see the same down here in the negatives. So this looks like not what we want. This looks like heteroscedasticity. If we do this for our log linear model, it looks a little bit better, less biased. The variance increases a little bit, or quite a bit, but not as much. So again, we'd say our log linear model is a little bit better in that regard. And then with the log-log model, again, we have more variance and some bias. So for now, we're sticking with this log linear model. Remember, you can just save these or copy them to put them into your answers worksheet, your Word document. Okay, now let's move on to number 6. For number 6, we're doing predictions of a house with 2,700 square feet. We've done predictions already, so we just need to take some code from up here. This is our linear model. I'm going to change this square feet with the value 2,700. Instead of generating a variable, we'll just display this. Predicted value of 2,700 square foot house. It's the linear model. When we run this, we get a 2,700 square foot house. It's $201,364 based on our linear model. And then when we do this with our L price, our log linear, we're going to need a slightly different equation in here, so let's go up here to remember what that was. It's the exponential. And again, we want to switch square feet with 2700. So this is our corrected predicted value. And then we want to do this for the L square feet as well. And compare the values. So in here we want to do ln of 2700. Since we have the log of square feet as our right hand side variable. And so when we run these, we need the sigma squared local variable in here too. So copy that. And run this. We get a house of 203,515. It's very similar. And then run it down here. We get 188,220 for our log model. Okay, so those are our predicted values for a 2,700 square foot house. The next part wants us to construct a 95% confidence interval for the value of a house with 2,700 square feet. Now, here we should remember that when we have a log on the left-hand side, our confidence interval is going to be done a little bit differently. We're going to predict the log of price and then take the exponent at the end. So let's get started with that. Also, we should remember that the variance of our forecast error is this big mess. Since we're predicting a single value and not an average, not an expected value given this x value, it's going to be a larger variance, and we have to use this formula, which simplifies to this one, which is easier to put in Stata. So let's just write that in Stata so we have it. So the variance of our forecast is going to be sigma squared plus sigma squared divided by n plus x naught minus x bar squared times variance of b2. So for the linear model, we will make a local x naught. This is going to be 2,700. And quietly regress price in square feet so we don't get all that output. If you want to see the output, just remove the quietly. And then our y naught, it's going to be simply this thing, and just put x naught here. It's the same thing. And then our local sigma squared. This is why we did the quiet regression, so we can get all these values from the regression stored data. And then we're going to quietly summarize square feet. That'll help us, that'll allow us to access the mean directly. And then here's where we're going to find the standard error of the forecast. Equals standard forecast error equals square root This is just a little tiresome to type in, but after we type it in once, we can just copy and paste. So x naught. Here's the mean of our square footage from that summarize command. And this should be squared times standard error square footage squared, which is the variance of B2. Standard error of the coefficient that goes with square footage squared, which is the variance of B2. And then that should give us our degrees of freedom for the forecast. And then to find our confidence interval, we just need to basically plug that into the formula for a confidence interval. Let's do display. A bracket in there. And we have y naught, because why not, minus our standard error of our forecast times the critical t value and VT tail of degrees of freedom from the regression. That's 0.25. Since we have 95% confidence interval, we want 2.5% on each side. And then the upper bound, this is the lower bound, the upper bound is just going to be the same thing with a plus. And then put the closing bracket in there. And hopefully when we run all this together, we spelled something wrong. So it's a common thing in Stata, make sure you check your spelling. Too many. Gotta be careful with our parentheses. Here it is. So I paused it to go through and fix the spelling errors. That's a big thing in Stata. If you can't find it, don't know your error, then more than half the time it's a spelling error. It can be really hard to find. So now when we run this, we get a confidence interval for the price of a 2,700 square foot house. So we would say we're 95% confident that a 2,700 square foot house will be priced between $141,801 and $260,928. So now we're gonna do this for the log linear and the log. So it's a very similar process, but we need to predict the ln of y and then takes the exponent, and our forecast error should be the same. So we have log linear I'll just copy all this and see if we can just manipulate it. So we have L price. This is the ln of y, will be given by the same, it'll be just our constant plus our B2 times 2,700 sigma squared. Gotta find that, quietly summarize, and then our standard error of the forecast should stay the same, at least the same formula. And then we have ln of y hat. And this needs to be exponential. And that of this whole value. So exponential of that, exponential of the upper bound, and let's see how that goes. So it worked. So we have slightly wider confidence interval, but telling us similar information. So we're 95% confident that the price of a 2,700 square foot house will fall between these two. And then if we want to do this for the log, then we will have to just change our square feet to log of square feet. If we change our x0 to log of 2,700, and that should be the same throughout. I'm going to summarize L square feet, and then this should all be the same. When you run this, whoops, missed this. Log of square feet. And when we run this, we get a slightly wider confidence interval, or slightly lower. Looks like it's based on having a lower prediction. So we're 95% confident in this model that the price of a 2,700 square foot house will fall between $122,000 and $277,000. Based on your work above, which functional form would you use? So this is where there's a little bit of interpretation. You want to explain yourself fully here, but based on the higher R squared value we got, the histograms of the residuals and the Jacques-Barré statistic, it seems like the log linear model confirms it fits our normality assumptions and gives us the best fit of the data. And that's because price tends to be something that's a skewed variable. So you have some very, very high prices, and then so since it's not normally distributed, it's right skewed, we tend to take the log of price, and that helps us get a better model, a better R squared, and a model that confirms our assumptions. So I hope you found this helpful, and feel free to leave questions down below. And remember, you can always change the speed of the video, pause, and go along at your own pace. So yeah, that's it for me.